I'll flow with it, and then you guys can edit it and do your magic to make me sound good and popular and like a god. That's what we were talking about before you guys got here. All right. With that note,
and this is actually episode 40.
I gotta cross my legs the same way, so we're all.
I break the pattern, man.
Chap, I'm gonna be honest though, Chap, you have like the politician leg cross. Like you look very like I can't. My leg doesn't bend like how do your hip work like that, dude?
Like the problem is I just fucked up my hip so much from playing baseball that I like this is as far as I can rotate my.
Because you have like most politicians like sit like this, where they're much more like extended. I'm like,
I would much rather sit like this. It just looks it
looks really dumb. Go back to the other way.
Inflexible and
stick with it. Yeah, it works.
Yeah. Thanks. I feel like you really got my best interest in mind. All right, welcome to episode 40 of Roid Rage. Today, by Matt's declaration, he becomes a god. That may or may not happen on this episode, but what will definitely happen is we will have Andy Ryan, our payload scientist, on to talk about what are payloads and why do they matter. Matt, you already look like you're going to say something.
Like that was the worst intro ever. You said we're going to have Andy on. He's here.
All right, he's here. Yeah, we are going to.
I'm here
we have
now,
not yet recorded the episode. He is going to be here. Rachel, would you like me to re-record that intro?
We've hit the like dementia part of the podcast. We've hit 40 now, and now it gets to the point where we're like,
to be clear, we hit dementia a long time ago.
We're continuing, chap. You've already gone too far.
All right. All right. Welcome to episode 40 of Roid Rage, where we are going to talk about payloads today. Matt has also said that this is an episode where he becomes a god. We'll see if that is going to happen.
I already am.
To be debated, but what we definitely have here is Andy Ryan, who is our payload scientist. He's going to talk about why payloads matter in the context of asteroid mining missions. But Matt is also going to give us a little bit of a history because Matt likes to wax poetic, so I'll give him the opportunity to do that in a minute. But before we get there, Andy, tell us who you are, how you became a payload scientist, and then we'll let Matt go on his journey.
And tell us why you have two first names.
You can blame my parents for that. I also have one in the middle too, so I guess there's technically three. But
what's the middle?
Oh, I can't for safety reasons. I can't disclose that. My identity.
I hope it's like Andy Bob Ryan.
Yeah, it's just Andy again.
Oh man, Andy squared Ryan.
Yeah.
Okay, I like it.
All right.
Anyway, so yeah, thanks. Happy to be here. So I guess I would describe myself as a planetary scientist.
Okay.
I went to graduate school to study planetary geology. And I got involved in payloads at that time because my PhD advisor was building the thermal emission spectrometer, which is a fancy thermal instrument that went on the OSIRIS-REx asteroid sample return mission.
Okay.
So I got to sort of shadow that whole process where they were going through the different design reviews and then eventually constructed that instrument, sent it to be on the spacecraft. And by then I got involved in the vacuum testing and qualification of the instrument and on its own, and then the instrument once it was on the spacecraft.
Yep.
Saw it launch, and then I finished my PhD, continued on analyzing the data from that instrument when the spacecraft arrived at asteroid Bennu. And once it collected samples and brought the samples back to Earth, I had the pleasure of participating in the sample analysis program. But I've always, I guess, had a special place in my heart for the instrumentation that goes into making a really excellent planetary mission, whether that's a science mission or an asteroid resources mission.
Got it.
Andy, what's the difference between planetary geology and just geology? Because isn't this a planet?
There is no difference by that definition. It depends, like some programs, the terrestrial geologists and the planetary folk mingle really well, but other programs they don't
question,
like to talk to each other as much.
Do you think you're better than a normal geologist?
Absolutely.
Okay.
Yeah.
Okay.
Good
That's the most important thing. So also so you basically said, hey, I've been to an asteroid before. You were the only person who's actually handled direct asteroid material that's not been altered by Earth's atmosphere, correct?
I'm not the only person,
only person in the context of AstroForge and definitely in this room.
But I guess I'm one of the privileged few. Yeah, it was a really amazing opportunity.
So then you just said you got to do it again and come here and do it?
Yeah.
Okay.
So we wrapped up our sample analysis campaign, wrote a lot of really exciting papers, and I was like, all right, how can we make this happen again?
Did you steal any?
No comment. No.
Cool.
The NASA police are going to knock on the door.
fuck is a payload, Andy?
What is a payload? A payload could be anything that goes on the spacecraft. Usually we think of it in the context of like the scientific instruments. So payloads are typically the science instruments that are designed to tell you what you want to know about the thing you're going to. So for an asteroid mission, really of any kind, the payloads are there to help you understand, what are the physical properties, chemical properties, mineralogical properties of your target asteroid. And, the payloads that you choose depend on what kind of questions you're trying to answer, but also the architecture of your mission. If you're doing a quick flyby, if you're going to do a rendezvous and spend a lot of time there understanding the surface, how close you're going to get, things like that. But payloads are just there to give you information, really.
Honestly, it's kind of weird we call it a payload. It's still part of the primary spacecraft. And when I think of a payload on, for instance, an aircraft, you think of ordinances or humans or whatever. Yep. It's something that like goes on and then is depleted from that. You either drop a bomb or you get off the aircraft. I guess maybe.
I've always thought of it as like it's something that paid to join the ride.
Oh, so you think of it as like paid?
I don't know. That's how I've thought about it. I don't know if that's
it's
right.
It's a paid load instead of a payload. All right. That's good to know.
Like, hey, I paid for my spot here. And then in some cases, that's exactly what happens. Some people, or some companies can pay to put an instrument on another spacecraft.
How many payloads were on OREX?
Like 4 or 5. There was a whole camera suite. So it's called the OCAM suite, and there was a narrow angle ranging camera, so that gave you the really high resolution images from far away. There was a mapping camera that gave you a few different colors. We had 2 different point spectrometers, one of them in the visible and near infrared part of the spectrum, another in the thermal part of the spectrum. There was a laser altimeter that told us how far away we were from the surface, but also created an amazing 3-dimensional topographic map. So we ended up having a model of the asteroid down to, I think like the final model was like 5 centimeters.
Whoa.
Like for the whole asteroid. Insane data product, huge file. And there was even a student instrument that was built at MIT, X-ray fluorescence spectrometer. So I don't know.
Did it work?
I forgot to count. It worked, but I think that they had some issues with the detections where they needed to integrate longer, and they ultimately didn't get a really strong signal, unfortunately.
Interesting. Yeah, it's this weird concept with payloads and what they mean and where the delineation is and even what the first one was. Before we started recording, we were talking about probably the funnest one to talk about, right? The Corona project. And these were film canisters taken. I believe it was a Kodak camera. I'm sure our viewers or our 4 listeners will fact check me on this. I think it was the same flight package as the U-2 that was flown, and images were taken and they were expelled from the spacecraft as literal film canisters and caught over the Pacific Ocean. Those were the first spy satellites.
So wait, the canisters themselves had to re-enter orbit?
Yeah. Canisters were re-entry vehicles that were put over, and then they were flown and picked up. I believe they were picked up in the air by helicopters.
That feels like a real haul.
I love that.
Yeah.
I mean, it's the same way. I mean, if you guys... ULA, when they were first looking at Vulcan, was going to parachute back engines and pick them up with helicopters, and I think it comes from that original Corona project.
Okay.
Right? Of course, you miss one, it goes sinks to the bottom of the ocean. Well, that sucks. You don't understand what's going on in Russia. But like, the Cold War bred some really cool kind of payload packages. I think these have very quickly shifted from. There's obviously the spy satellites, and the reality is even if I did know about them, we can't really talk about them. But I also don't know about them, so it's not very helpful.
Yep.
Are going to be, I'm going to assume, a lot of film and probably a lot of RF stuff to determine what's going on around the world. Scientific payloads, though, are kind of very different. Who builds them, Andy?
Scientific payloads are built by, a lot of them are built by universities nowadays. There are other companies that built them. Some of them start out, as research labs or spin-offs from research labs, and they go through, changes over the years. Like, for example, the thermal instrument that was built on OSIRIS-REx was built at Arizona State, and a lot of the engineers that came to Arizona State to build that instrument formerly worked for other scientific instrument firms, out in California. And so, people kind of move around and develop these really like bespoke skill sets to make these specific instruments. So a lot of scientific payloads can end up becoming really expensive because you're using, really high quality customized like detectors and parts, But a lot of the expense is in the engineering labor, just because there are very few people that know kind of, the secret sauce that goes into the design of a lot of these instruments.
What was the university overhead?
Probably about 50%.
What's your favorite payload?
What's my favorite payload?
There's one correct answer, by the way.
Oh, gosh.
If you get it wrong, you might be going back to Arizona State University of A.
Yeah, I've been at all the Arizonas, so you can send me back to any one of them if you want.
One of the three.
Oh, man. I don't know if I can. I mean, I'll say the one that I've worked with the most. That'd be the OSIRIS-REx thermal emission spectrometer, which was obviously on OSIRIS-REx.
You just started saying words.
Yeah.
Can you explain to us
Absolutely.
in human terms what the fuck that does?
Yes. So a thermal emission spectrometer, I'll break it down. First thing it's measuring the heat off the surface of the asteroid. So every surface that's not at 0 Kelvin, absolute zero, is emitting thermal light, basically. Our eyes can't see it because we can only see in the visible portion of the spectrum, the electromagnetic spectrum.
Humans are dumb. Yeah, I get it.
Our eyes kind of suck. Yeah. So, but if you go out to, longer wavelengths beyond visible, you go into near infrared, you eventually end up in the thermal spectrum where everything is glowing. Okay. And so you can make detectors that can see at these wavelengths. So the thermal emission spectrometer, it's measuring thermal emission, that's that glowing light. And the spectrometer part just means it's measuring that light at lots of different wavelengths or frequencies. So our eyes, we see red, green, and blue. This is measuring at something like 100 different discrete wavelengths, all the way from 5 to 100 microns. So think of it as like it's measuring a fingerprint. Just like we can learn a lot about a material just based on the intuition we've learned by looking at like the color. Like you can look at your blue jeans and we know that those are blue jeans just based on like the color and texture. You can kind of do the same thing in different parts of the electromagnetic spectrum. So you go out into the thermal infrared, you find that a lot of materials, like different minerals that make up rocks, have distinct diagnostic fingerprints. We call those spectra. And you see all of those overprinted on each other. You measure that. You kind of take the data back. You compare it to spectra you collected in your lab of the different types of minerals you think might be on the surface. And you basically are just kind of playing the quantitative matching game, saying like, okay, well, what we measured, it looks like it's a mixture of clay minerals, and there's some magnetite, and there's some this and that and the other, and you're able to quantify their abundances and learn a little bit about what the asteroid is made of and its history. So that's what that instrument did.
So you literally just made night vision goggles?
Yeah. And there's more to it than the spectroscopy, actually. So the whole night vision part, this is the part that I really like. So just from the temperatures alone, you can learn about the structure of what's on the surface of the asteroid. Based on how much it heats up during the day and then how much it cools off at night and how quickly it does that. Like the analogy I like to give is when you go to the beach and it's a really warm day, the sun is shining, not a cloud in the sky, and you put your bare feet in the sand and you immediately are like doing the tippy toe dance, run into the ocean because the sand is so hot. But then you step on the boardwalk or you find like a nice, like maybe there's a boulder on the beach and that's nice and cool during the day. You flip that, you go out at night, the sand on the beach has gotten really cold, but the boulder or maybe the brick wall of a building next to the beach has retained its warmth. And so this is something we call thermal inertia, or it's basically a material's resistance to temperature change. So we use that on asteroids where if something heats up a lot during the day and then cools down a lot at night, that's an indicator that it probably is a poor conductor of heat or it's low density. It could be like a fine powder. Vice versa is if it heats up only a little during the day, cools off only a little during the night, that might be like a more competent, coherent, solid rock material or metal in the case of AstroForge's mission. So that's like one simple way you can have another little diagnostic index of, okay, what the heck is on the surface of the asteroid without actually having to go down there and send an expensive little lander probe to poke around and do like all sorts of material properties measurements. So it's like each technique gives you a clue. Like there's no one instrument that's just going to tell you 100% of what you want to know, but each instrument on its own is giving you, it's uncovering just like a little part of the story, and it's usually the combination of multiple instruments and that's why OSIRIS-REx had like 5 or 6, or because you need that combination to really answer all the questions that you're asking.
And so when you talk about like the OSIRIS-REx like mission architecture, did you start with, hey, here's what are the samples that are available, or sorry, the sensors that are available, so therefore here's what we're able to do, or did you start with here's my wish list of everything that I want to be able to do, and then sort of pare that down by what's practical given some number of constraints?
Yeah, that's a process that you have to go through for designing any mission. And so I didn't participate in the payload selection for OSIRIS-REx. That predated my involvement, but it's a little bit of both. You do have science questions you want to answer, and these missions are always driven by some set of science objectives. So you lay out your objectives, and then you do have to ask yourself, okay, how can I answer these questions? And like, what is actually available out there? We can't send like a giant mass spectrometer there because that technology just doesn't exist yet. So, okay, so if you're someone like the PI of OSIRIS-REx, Dante Loretta, he was probably thinking, okay, all right, so we're probably going to want some spectrometers because that's going to give us mineralogical information. Okay, who do I know that's out there that makes spectrometers? All right, well, Phil right up the road, he makes a thermal emission spectrometer, so maybe I'll jot him down as a potential. And you kind of create a short list. You start gathering information about the instruments that are possibilities, and then you have to think about practical constraints.
Got it.
Cost, power, mass, timeline, risk, all
Not
that
cost.
stuff. Yeah.
How far away? So you mentioned that you don't have to get down and take a sample for this instrument to work and some of the others. How far away could you be to actually get valid data from that sensor?
So that'll depend on the optics that you put on the instrument. So, how big of a telescope do you put on it? The further away you are, you can keep putting a bigger and bigger telescope to collect more photons that are basically coming off your target. Eventually, you're going to run into issues where your telescope is bigger than your spacecraft. So, there's a limit there. And then the detectors themselves will have a sensitivity. It's often thought of as like the signal to noise ratio. So it's, for whatever you're trying to measure, and for spectra, it kind of, if you look at like if you do a Google search for like a thermal spectrum, it'll just look like a little wiggly line. And your question is, okay, how big are those wiggles compared to just like the random white noise that you get from the instrument? You want to make sure you can discern those wiggles and they're not just dwarfed by noise. So it's a combination of those factors.
Who made that? So I'm assuming you have some kind of like sensor like I'd find in a camera. Is that the right way to think about the sensor you had?
So for thermal spectrum, you need different types of sensors than you would use for a camera that operates like a regular cell phone camera, or the cameras that are going to be on Deep Space 2, for example. Thermal, there are several different types of detectors. A really common one for like a thermal camera, like night vision camera, would be what's called a microbolometer. And those are just like, they're literally like, it's an array of little black squares that absorb the energy really well, and their temperature literally changes based on, the heat that's emitted from your target. And it changes each one of those little squares' temperature, and then you electrically measure their temperature. The OTES instrument on OSIRIS-REx has a pyroelectric detector, which honestly, I don't think I could explain how that one works right now, but it's, there are lots of different types of detectors.
Who built it?
out
Was
there.
this something that could be hand built, or is this made like an ASIC, like a chip?
Yeah, detectors are, especially thermal detectors, that's a really like specialized thing. There are different groups across the country that are able to manufacture them. So like for thermal detectors, a lot of groups have been using INO, which is a company in Canada that makes really nice microbolometers. Teledyne, which I think acquired FLIR, and FLIR is one of the most common commercial makers of infrared cameras. I think the pyroelectric detector on OTES, I want to say that came from a company in the UK. I don't remember exactly, but yeah, there are bigger manufacturers that make like kind of the commercial quality detectors. And then when you get to the really sensitive ones, or the ones that are radiation hardened, that's when you get into these companies that are more specialized, or in some cases, even the big aerospace companies. Like some instruments have thermal detectors from Raytheon, for example.
If there's margin, Raytheon will be there. Okay. I'm a little lost on what this looks like, but I got you. Who made the lenses and the telescope that was on this detector?
That one I don't know. Sorry.
Worst instrument scientist ever.
I didn't build OTES. I was there for the ride as a grad student, so I know some of it, but not all of it.
Well, I mean, maybe that's a good transition of like you are now here as we are in the process of building Deep Space Two.
Yeah.
Obviously, you weren't involved in sort of like the mission architecture of Deep Space Two, but you are now sort of in charge of, okay, we need to collect some amount of data.
Yep.
So I guess let's start with what's the data that we do want to collect, and then how does that map back to here's the instrument cluster that we're going to fly on that?
Yeah. So really good question, and it does make sense to start with the question of what do we want to learn?
Yep.
What are we trying to do? So for Deep Space 2, it'd be great if we could confirm that the surface is metallic, either metal rich or 100% metal.
Mm-hmm.
Or 100% platinum.
Yeah, 100% platinum. Even better.
That works too.
We're targeting we have a whole list of potential bodies that we could rendezvous with.
Mm-hmm.
But the data that we have from telescopes, we can't be certain what we're going to find when we get there. So step one, what do we have in front of us when we get to the asteroid? So that can partly be accomplished with just good old-fashioned cameras. Just take a look. What does it look like? Do we, is it smooth and shiny? Do we see heterogeneity on the surface, like where there's some areas that look smooth, some areas that look rough?
Andy, hold on, time out. This is a podcast that normal people listen to.
Okay, so I can't
Can
use
you
the
not
word
use words like
heterogeneity.
heterogeneity, whatever the hell you just said?
All right. Is the surface all the same, or does it have differences on it?
This is what I hate about geologists. It's like they're like, oh, same. Let's make that called heterogeneity, whatever the word is.
Pretty sure the geologists didn't invent that word.
Yeah.
Jesus Christ.
I'm not a geologist, and I use that word all the time. So,
All right. Is the surface does the surface look the same or not?
Really?
So there are like areas that are smooth. Do we see rough areas? Because if you see like diversity on the surface, oh wait, I can't use that word. I can't cancel. If you see variations on the surface, that might tell you that like, okay, this might be a mix of stuff, or it's had some surface processing or whatever. Even just measuring the reflectance. Like if we can get a calibrated like measure of how reflective it is, that might tell us the metal content. If it's very reflective, it's a good indicator.
Okay.
Beyond that, that's when we would start to look into some of the spectrometer options that I was discussing earlier, even just like a good old-fashioned thermal imager, because if it's highly metallic, that should show up in the thermal signature, and we have some idea of what the spectrum should look like if it's dominated by metal versus dominated by other just common minerals that you find in non-metallic asteroids. So, but the game's a little bit different here because we're not building a, tens or hundreds of $1 million NASA mission. So we can't necessarily afford to send a $15 million spectrometer and a $10 million this and a $10 million that, because on the big, flagship and New Frontiers and whatever NASA missions, that, those are kind of the typical price points for some of these like really high quality, guaranteed not to fail science instruments that are one of a kind. And
so
Deep Space
just
2,
to put that in perspective, like that's basically more than the cost of spacecraft we have right now.
Exactly.
Yeah.
We're not going to put an instrument on a spacecraft that's more expensive than the spacecraft itself.
But we do have an advantage, which is when most of these missions are designed. I don't know when the paper was first written or the proposal was first written to OREX to when it got to Bennu was how long?
When the mission, when it was first proposed, or when it was like selected?
When it was first proposed to when it, to when it got there was
I think it was announced that NASA picked it in 2011 and it got there in 2018.
So it was a 7-year mission.
7 years to get there.
In a lot of these cases, and that's a pretty quick timeline for NASA, to be clear. A lot of these are much, much longer. If you look at like James Webb was, from the mid-90s to whatever. Some of these things really drag on, which means the technology that is selected for things like the imagers, in a lot of cases, it's very dated by the time it actually flies. So the nice thing we have and the advantage we have is we get to use a modern imager, which means we get much more pixel density than you were to get if we were to pick a camera from 5 years ago. In fact, we also now have, so take it through cameras a little bit. There's 2 types of sensors. One's called a CCD and one is called a CMOS sensor. A CCD sensor has a really nice feature where you can read it all at one time. It's called a global shutter. And so if something is going really fast through the frame, you can take a picture that is developed just like you were to take it on film. There's no drag. If you've ever noticed on your cell phone and you move really quickly, you'll see lines develop on it. That's because a CMOS sensor is read line by line. So like if you ever see a picture of a phone thrown out of an airplane, I did this, don't ask me why, but you get it and you'll notice it just becomes like a big blur on the screen. And that is actually the read speeds of the CMOS sensor. CMOS read speeds have gotten extremely fast. And so because of that, we can choose CMOS sensors, like we fly on deep space too. It's a Sony Aptiva sensor. It's got a 10 nanosecond read time from the first line all the way to the last line. That is really, really quick and gets rid of that blur, which now means I can fly a 20 plus megapixel imager that I could not have flown even 2 years ago or 3 years ago or 10 years ago, for sure not, as we go. So we can get really pixel dense imagers that allow us to do these things. The problem with spectrometers is that they're not developed for cell phones. They're not developed for small cameras are everywhere, right? Every device you have has 40 cameras in it for some reason now.
Yeah. And
that's really pushed the development of those sensors. That hasn't happened on spectrometers.
Yeah, with spectrometers, there are definitely still some challenges there. You can kind of think of like the two parts of the spectrometers. There's the detector, and then there's all the optics that are splitting the light, in essence, into the different wavelengths. And so the spectrometer part, we could design something like that, and the pieces that go into that aren't necessarily that crazy expensive, but you need a good optical engineer to come in and help you with the design and do all that. The detectors, I think, is where we can take advantage of some advances, even if we don't have a full spectrometer in the cell phone. Like coming back to the example of the thermal detectors, those have come a long way in the last 30, 40 years. There are now microbolometers that can fit in your cell phone. And that, 30 years ago, is just absolutely unheard of.
That's because of night vision, Andy.
Yeah.
It's because of Call of
military.
Duty.
Yeah. And so now we have the option and the idea to, okay, let's go buy a commercial off-the-shelf FLIR detector, and we can put, a grading spectrometer assembly in front of it, and, we can build up an instrument that maybe for parts alone is going to cost, I don't know, upwards of, a few tens of thousands rather than just for parts. We got to figure out the design rather than millions of dollars.
Why do we always add the off the shelf? Where's the commercial not off the shelf?
I guess it would be if it's commercial, but it's built to order.
Isn't that the not commercial?
I don't know.
No.
Like you don't go to the grocery store and this bread is on the shelf. Right? Just trying to think when you go commercially.
I didn't make COTS the acronym, man.
I never understood this acronym. Why do we need to add off the shelf? You also can't go to the grocery store and buy a infrared pyrometer off the shelf. So it's always made to order.
I would love it if there was a little store where I could browse thermal detectors.
Yeah, fair. Maybe at Erewhon with my strawberry.
We need that.
But I think it's actually by saying it's commercial off the shelf by definition means it sure as hell ain't off any shelf. It's not commercial either.
It's off their warehouse shelf, I guess. I don't know.
Yeah, with the 18 to 36 month lead time.
Matt. I don't know. I don't know what to tell you.
There's a long list of shit that's bothering him, so you'll just don't worry about it. All right, so you've talked about image-based data that we want so far. Mm-hmm. What else do we want from a data perspective? And also I'm going to point out, it sounds like everything that you're talking about from a data perspective is assuming some amount of distance between us and the asteroid.
Yeah, so the instruments I've talked about so far are you could, collect those images from anywhere out, hundreds of kilometers out to as close as you want. Yep. Once you're able to get down and touch the surface, that opens up a lot of new possibilities. People are there's a lot of instrument design going on right now for lunar surface exploration. So we've been seeing a lot of creative ideas coming out of there. Like, for example, you could consider something like an X-ray fluorescence instrument that is going to measure the elemental composition of the surface. With something like an XRF, there are kind of two ways to do your measurements. You can either, because the way that this technique works, you have to emit X-rays into your sample, and then it, I don't know all the physics behind it, so I'll just use the name. It fluoresces, and you measure the fluorescence, and that tells you the elemental composition.
Sounds like a geologist.
Yeah, nailed it. You can use X-rays, coming from the sun and from space to do that for you, and you can try to measure from far away, but you got to sit there and measure for a really long time. You got to sit and stare, collect.
Yep.
But if you get down to the surface, now it's much easier for you to bring your own X-ray source, zap the material that's right at the feet of your spacecraft, get a measurement, understand, okay, what are we looking at here? What's our iron content? What's our nickel content? Is this what we want? You can try to do magnetic measurements. You can even get into doing experiments, like kinetic experiments.
Didn't Laddie do this?
Well, there was the
What's the one that we just flew into the moon? We said fuck it and crashed it.
Yeah, there was the L-Cross impactor, where they basically there was an area on the moon that scientists hypothesized, which means they believed had water, ice. And so they basically sent a kinetic impactor, slammed into it, created a big plume, and then, they used all the fancy spectrometers and stuff to measure the spectrum of all the dust that came out, and they confirmed that there was indeed, about like 5% ice there.
I went to an amazing talk by Bethany Oakman, who was the PI for Lunar Trailblazer on water ice on the moon. And I'm going to paraphrase her talk that I didn't fully understand because it had lots of words in it. That have we actually discovered water ice on the moon, or have we just detected the constituents for water ice, and there's some misleading information about what structure it's in?
Oh boy, I'm gonna get myself in trouble with the lunar community here if I don't.
That's the whole point,
right.
Andy.
Yeah,
yep, that's the whole point. You're a planetary geologist.
I would say that I think that we have detected it, but it depends on like how conclusive of a detection do you need to say, like, do you need to get before you say, yeah, we've 100% confirmed it? Like, we don't have a sample. We've never gone there and like poked it and be like, that's ice. We haven't taken it back yet. That's the goal. That's one of the objectives of like the Artemis mission and some of the upcoming robotic missions, is to actually collect samples, be able to bring them back and like confirm all this.
So we should, by like 2050, we should figure out if there's water ice?
Yeah.
Okay. That was a very non-answer.
But there are other kinetic experiments that you can do, and that have been done on asteroids. So OSIRIS-REx, when it collected samples, pushed into the surface for a few moments before it fired a jet of gas to basically deliberately stir things up and grab the sample. But during that, it was basically 1 second where they pushed into the surface. We were able to measure the force, that the surface exerted back on the spacecraft, and learn a lot about the structure and how basically easy it is to move the material around, just from some modeling with the data. And so they're planning to do that again with the OSIRIS-APEX spacecraft, which is just OSIRIS-REx 2.0, when it gets to the asteroid Apophis.
To be clear, it's not OSIRIS-REx 2.0. It's just OSIRIS-REX renamed.
It's renamed, yeah.
Yeah, you can't call that 2.0. It's not a second iteration. They just literally changed the name.
They did, yeah.
Why did they change the name? And it was so... OSIRIS-REx was way cooler because it sounds like a T-Rex and shit, and they're like OSIRIS-APEX.
When we were...
what happened?
When we were considering the rename, we had an internal poll where people could suggest any name that they wanted for OSIRIS-APEX. There were some really like creative... it was like OSIRIS-REx 2 Tokyo Drift, I think, was one of the suggestions.
I mean, that would have been amazing. That would have been way better than OSIRIS-APEX.
Yeah, you'll have to get Danny Delagostino on the show and ask her exactly why they went with the full rename. I think they just wanted to make it clear, like, this is a new mission. We're going to a new asteroid, and so let's call it something new.
To be clear, the Bennu, when Bennu went down and touched the surface, when OSIRIS-REx went down and touched the surface of Bennu, it was not what they expected to see.
That's right. We were pretty surprised when we got to Bennu, and so this shows how you can pour a lot of resources into using ground-based assets to analyze an asteroid, or even space telescopes, and try to predict what you're going to see when you get there. And just because we haven't been to many asteroids yet, they are surprising us.
Yep. I think it's also a really good reminder of how NASA designs spacecraft and how robust they are. I mean, my understanding was we thought Bennu, when we got there, was a cohesive asteroid, and when you touched down on it, it was not, right? It was a rubble pile, and there's different areas where we found out that was true or not. And
yeah.
But what's important to understand about the way NASA designs this is there is so many backup plans for how these missions work, and so many contingencies. And it's a huge luxury NASA gets, and that's kind of why you see the price tag where it is that mission was a $1.2 billion mission. We have none of that shit.
Yeah. It's a really robust spacecraft, and yeah, when we got there, we had the ability to kind of take a step back and be like, all right, how can we make this work with what we have? And fortunately, there were a lot of options. There's the ability to update the software that was used to go in and touch the surface, lots of different things. And yeah, we won't have that. So,
Well, to be clear, we can update the software.
Yeah.
okay, well,
We have that. All right. So what do we have then from a sensor perspective? Like what you're in charge of speccing all of this out.
so for Deep Space 2 right now, it's currently visible cameras.
Okay.
Yeah. But we're looking for other payloads. And I think Robin got doxed on like episode 1 of this podcast because he was asking for payloads from JPL.
Yep.
So I'll re-echo that call that like we're open to interesting payload ideas from people out there.
That are low cost, lightweight,
low
cheap.
cost, lightweight. Actually, negative mass. If you can make that happen, that would be really
prefer
helpful right
negative mass.
now. If it can absorb heat, that would be great too. Solve some of our
It's a little
problems.
bit of a radiator. But then also when we're not firing the thruster, it can not be a radiator. That'd be cool.
Yeah, it'd be
Yeah.
great.
Yeah.
Okay.
So yeah, because Deep Space 2, like we're starting to approach the finish line. I think our options are a little bit limited right now, but I am looking into a few opportunities for some multispectral payloads or a thermal imager, things like that. So TBD there. And then beyond that, I think we'll have a little bit of more. We'll have more time on our hands to consider.
If I could wave a magic wand and give you an extra 5 kilograms, and let's not worry about budget, what's another instrument that you would want to fly?
I think a spectral imager, either near infrared or thermal infrared.
Why is this always the answer from scientists? Every time you give them like, oh, budget doesn't matter, cost, they always say
Spectrometer.
spectrometer. They always don't classify what type of, there's like spectrometer.
Well, maybe
It's
he's about to
exactly what it is.
classify.
Okay, what type, give us some fucking details, Andy. What kind of spectrometer?
Vis-near air spectrometer, like 400 nanometers to 2,000 nanometers, 10 nanometer spectral resolution, imager that's able to resolve the surface at, a meter per pixel. Screw it, 10 centimeters per pixel, a centimeter per pixel, 1 nanometer spectral resolution. Hey, you have to.
Yeah, I mean,
magic wand, baby.
Yeah.
Let's go for it. Actually, make that instrument go all the way out to 100 microns. Let's
Okay.
cover the whole visible out to thermal infrared wavelengths. Beautiful spectral resolution, beautiful visible resolution. We'll put a magnetometer on there. So if we touch the surface, we'll see if it's magnetic.
Tim Cook, if you're listening, please put that in the next iPhone 18
Yeah,
so
thank
we can
you.
actually afford it.
Yeah.
Okay.
Yeah, there are a lot of things that I would love to put on a spacecraft, and you always just run into what's available and how much is it going to cost, how heavy is it, how much power does it require, and that's where you got to make the hard decisions. And so we're making those hard decisions now.
Got it.
Yeah.
Awesome. Andy, thank you very much for detailing what you would want. If I could wave the magic wand, I will let you know when I manufacture said magic wand, so you can actually have all of that on the spacecraft.
Thank you. I really appreciate that.
I'm here to support the payload scientist community. That's all we have on payload today. Just to remind you, as a guest, you have the opportunity to ask, preferably Matt, but I guess technically me as well, a question at the end of our mailbag. So please let your question ruminate. With that, we're going to go into mailbag. Today we have question in many parts. This is from Sean. I am one of your 12 listeners that's excited about
we
your
increased?
company.
We grew 3x? Holy shit.
I like that he's saying he's part of the subset of listeners that's actually excited about our company, assuming that we have some listeners that are not excited by it, which I have a question of like, who is not excited about AstroForge, but also going through and listening to our podcast. But more importantly, he has enjoyed listening to some of the challenges we face every day. His questions, Matt, I'm going to ask you these in rapid fire. What softwares do you usually use for math, and how do you typically present results?
For math?
Do you do math?
Okay, hold on. Time out. What software is there's two ways, like modeling math or like performing math on the flight computer?
I don't know I can't specify, so you have to answer at that level.
Okay, all our math done is using the libblast library written in Fortran.
Okay. In Fortran?
Yeah, that's what it's written in.
Okay. What is your process for identifying independent parameters and then modeling the probability distribution? And he lists out a bunch of distributions that we don't care about.
Of what?
Is that like a question
Just like
from
hold on,
Lake's
what?
episode?
Hold on, what is the process if I didn't?
It's not like I'm misrepresenting these questions.
Okay, I think this guy's a GNC engineer that comes down to it. So what I'll say here is that all of our GNC code is prototyped in Python.
Okay.
That's what we use. And what is our process is when we talk about going into a Monte Carlo and running initial conditions, like we do actually, and same with our, when we do our trajectory planning, we list out everything along with its PDF, its probability distribution function to determine, is this Gaussian, is this linear, is this some multimodal thing we need to be really concerned about? In most cases, these are just going to be Gaussian distributions that we use, and we assign whatever the mean and the sigma deviations are. Like that's really it, and then we go into our models with it.
Okay. What is the best method, in your opinion, of reviewing complicated math to avoid making dumb mistakes?
Yeah, I actually find there to be a couple. Number one is you want to look at Monte Carlo results. They'll tell you a lot. And especially when you understand the inputs to the Monte Carlos and you see the graphs, you can clearly see if like, yeah, this is converging, or no, these inputs make no fucking sense. Of course it's not, or of course it's converging. Like you started with 0, right? And added 0. It doesn't help. But number two is one thing I've really started to push the team on is to show me visual simulations. There is always these weird edge cases or weird things. And guess what? If you come up to our office, you're going to see a spacecraft flying on screens all over the place. Those are real Monte Carlo simulations being played. And the reason for that is just so we can look at it and say, does this look right? I mean, if you look at an airplane flying, it's pretty easy to tell, like, yeah, that looks about how an airplane should fly. If it's flying upside down, you can be like, oh, we got in some weird area we need to go fix. And a lot of the actual issues we've had have been so erroneous that you're like, hold on, why is the thruster firing backwards, right? Like, you can see them visually really easily. So those are the two techniques.
Okay. And then last, how many simulations do you run, and how do you determine what's an acceptable confidence level of risk?
Yeah, right now the team, I believe, runs 100 Monte Carlos, which is probably not enough, but that's where we're at right now, and that still requires a lot of processing power. I'll say this, though. You can look there, and we could come up, I can come up with whatever numbers I feel are acceptable or what not acceptable. It's not actually how this works. Like, we have a really, really exceptional GNC team. Armand has built a lot of spacecraft and worked with this for a long time, and the NOBL is like, I really trust him to get it right. And you kind of have to trust your team to get these things right. So I'm going to go look at it. I'm going to ask some questions there. But at the end of the day, like this risk posture, he knows how we're trying to think about. He knows what the time frame is he has to get this all done. And then I actually want to take the least amount of risk possible in the time he is allocated. And depending on where we get, that actually could mean different things. It might not mean that we run 1,000 Monte Carlos instead of 100. It might mean, oh, actually Armand spends all his time testing the reaction wheels on the spacecraft or something. Like the risk isn't just quantifiable with an algorithm. You really got to be objective to what you're looking at.
Got it. All right, Andy, you're up. What is your question, preferably for Matt, or also potentially for me?
Please ask, chap.
Matt, if you were invited on the show Hot Ones, how do you think you'd do?
I'll be honest. Because I have a massive ego, I would go through all the wings very quickly and be very unhappy. But I will say this, that we had a guy leave Virgin Orbit, and so I took him to this place that served death tacos. And I don't know what they were, but, you know, it's the whole, like, it's 1 billion Scobles and shit, and I ate a death taco, and by ate, I mean I took a small bite of one. I literally went home and fell asleep for 12 hours and was in just, like, excruciating pain like I never felt. I thought when you ate hot shit, like your mouth was just going to burn. I'm like, oh, I could deal with mouth burning. I didn't realize it was going to feel like someone was stabbing my stomach indefinitely for a day, and all my lifeblood was going to be sucked out of my body. So, I mean, it really felt, I thought I was dying, and I kind of wish I would have died. It would have been easier, but it was terrible. I've never just left in the middle of the day and been like, I'm leaving. I have to go. I don't care. Fuck you all. And it sucked. And it wasn't even like, so I wanted to enjoy it, but
All right.
I would do it.
You heard it here, Sean Evans. Let's make that happen again.
Right.
Oh, I mean, this is now clearly we have to do a Hot Ones ripoff in this episode because,
No, we haven't reached, look, when I get more famous than Lewis Hamilton, I'll go on Hot Ones.
that's an absurd bar.
Exactly. So I'm not going on Hot Ones.
All right, cool.
All right. Thanks.
All right. Well, that is a great question to end this episode on. Andy, thank you for walking us through everything that it goes into designing a payload and what we're actually going to fly in Deep Space 2. Matt, thank you for exposing your Achilles heel, and now we know what we're going to do. We will catch you next week.